Alrighty. Hello and welcome to your Monday, our Monday. You've been doing your Monday, I've been doing my Monday. Now it officially becomes our Monday. So we are going to be continuing with our discussion of Chapter 4, specifically acid-base reactivity. The one piece of business that that I want to cover is this exam 2. Oh, happy Monday, Emma. It is a happy Monday. You know, some Mondays are like a drag. Or like you're tired or whatever, but then some you're like, I'm ready to get into this new week. That is the vibe that I have today. So with exam 2, I will be posting I'll be posting about exam 2 today on Canvas. Again, the same thing that I did for exam 1 and the prereq exam. I'll give you the points breakdowns of topics. So you'll help that will help guide how you allocate your time, what you spend your time working on, studying on. What was I gonna say? There was a thing. Oh, right. It's I know I've said this before, but it covers everything through everything through chapter 4. All right. The specific problems, specific materials will all be based on chapter 4, but the reason why I say everything is there is some sense in which this class is cumulative, right? Just because chapter 4 doesn't explicitly teach sig figs doesn't mean you don't need to know how to apply the rules for sig figs to get the answers correct on this exam, right? So there's things that we carry through, obviously sig figs, stoichiometry, but the specific focus will be the chapter 4 material: solutions chemistry, dilutions, precipitation reactions, redox reactions, acid-base chemistry. So, and again, if you're like scrambling to write it down, don't worry, don't stress. I'm gonna post in gory detail the points breakdowns, everything you need to know. Yes, Jared, great question. It will go live this Friday at 12 a.m. Exams always open on Fridays, and I believe they close on Mondays. I'd have to consult the syllabus. So it will be available as of 12 a.m. this Friday, and yeah, we've got 2 office hours between then and now. So so you can hit me up for questions and helps. Also today, in at 7 p.m. I am going to be doing part 2 of the chapter 5 lecture. All right. And again, chapter 5 is not on exam 2, but it will be on exam 3. So all that to say is you can watch it tonight live, ask questions live, or you can wait till after you take exam 2, but you'll have 2 lectures to go back and check. I've named them. When you look in the lab playlist, channel playlist, it says chapter 5 lecture plus office hours for these 2. So anyways, if you're not watching them live, you'll want to go back and check them out at some point. Kiev, great question. So Kiev, or yeah, I'm not exactly sure how to pronounce it. Asks, is doing chapter 4 book homework good prep for the exam? I would say that it is, but don't. Oftentimes, and I'm not saying you're doing this, but I've had students in the past ask, "Oh, is doing the homework good prep for the exam?" And I'm like, "Yeah." And then they take the exam and they're like, "There's stuff on the exam that wasn't in the homework." Of course, there's going to be. I'm going to ask you problems that you've never seen the specific form of. When you're studying, you should not memorize how to do a specific problem. The focus should be on understanding how a problem works, understanding what's being asked, and how these things relate to each other. Because I'm going to mix them around. You're going to see things on the exam that I've never done in lecture and that are not presented in the book, because I want to test on, do you understand it, not can you copy steps that you've seen someone else do. So the best way to study for exams in this class is do as many problems of different types as you can. So totally do the book problems, but also take any topic and Google that topic Gen Chem worksheet, and Google will spit out a ton of PDFs. Some of them will even have answer keys, and do those. Try them. Do problems written by other people, because the more formulations of these concepts you see and the more varied the problem pool that you work from, the better prepared you're going to be. So doing problems, solving problems is the best way to study, because that's what you're going to be doing on the test. There aren't any short answers on the lecture exams. It's all working problems. All right, and again, I'll be posting a little more about the specific concepts that go into the problems later today. All right, so with that being said, let's go ahead and jump into, or continue in chapter 4 with our discussion of acid-base chemistry. We'll see. We might finish chapter 4 today, though. I'm not 100% sure. Okay, so just a little bit of recap. At this moment in time, we know what an acid is and what a base is, right? And even though we talked about both the Arrhenius definition and the Bronsted-Lowry definition, in Gen Chem, we typically talk about acids and bases in terms of the Bronsted-Lowry definition, primarily. What's funny is in OChem, you'll learn another definition, the Lewis definition of an acid and base, and that one dominates your discussion in OChem. But for Gen Chem, we're very proton focused. Acid is a proton donor. A base is a proton acceptor. All right? And so with that knowledge, we're ready to look at our first type of acid-base reaction, and that is, actually I just wrote this and I'm going to get rid of it, because we're going to look at neutralization reactions. All right, we're going to look at acid-base neutralizations. And an acid-base neutralization looks like this. You have some generic acid, HA, all right, and this would be an example of just a monoprotic acid, which means there's only one proton to donate. Sulfuric acid, H2SO4, would be a diprotic acid. Phosphoric acid would be a triprotic acid, H3PO4. So there's our monoprotic acid, HA, and this, as I've said, is our acid. In a neutralization reaction, reacts with a metal hydroxide base. So some metal cation paired with our hydroxide anion. So this is the base in the neutralization reaction. You'll notice I put a question mark for the phase. Whether or not this is soluble or insoluble depends upon the metal, right? Hydroxide is mostly insoluble, but it's soluble with a few things. So whether we put solid or aqueous depends upon what that metal cation is. And in a neutralization reaction, these two react to form always two products: liquid water and a salt, which Could be aqueous or solid. That'll be determined by our solubility rules. Now this salt, right here, as we already know, salt is a generic term for an ionic compound. And the anion, the formula for this salt, will take the formula. It'll be made up of a metal cation, and the anion that's left over after the acid donates its proton. All right, so it's going to be some ionic compound where the metal cation from your base is the cation for the salt, and the anion for the salt will be whatever is left over after the base strips away all the protons from the acid in the reaction. All right, so let's do a couple of examples to kind of get our feet wet for these neutralization reactions. So let's write a balanced chemical equation for the reaction between, for example, let's do chlorous acid. Oops. Should be an H. Chlorous acid. And sodium hydroxide. All right, so now here's the thing. Professors love neutralization reactions because we don't have to tell you what the products are. We just have to give you the reactants, and that is enough information for you to be able to solve this problem. It's enough information for you to solve because the products are always water and a salt. All right, and we have to figure out what that salt is, but we can do it, and here's how. First, we need to write out what our our reactants are. So chlorous acid, we learned acid-base nomenclature last time. If something ends in "us," that means it comes from an ite. All right. So this acid structure is based off of the polyatomic ion chlorite. All right. Chlorite is ClO2 with a charge of -1. Now, the way you take your anionic structure and determine your acid's chemical formula is you give the anion one hydrogen, one proton for every negative charge. So if chlorite is ClO2 with a charge of -1, chlorous acid will be HClO2. All right, and acids in this in Chem 400 always going to be in the aqueous phase. All right, so you always throw that thing in the aqueous phase. Chlorous acid plus sodium hydroxide. Now sodium has a charge of +1, which we can determine from the periodic table. And hydroxide is a polyatomic ion OH -1. So since our charges here are the same, right? +1, -1, equal and opposite, I guess I should say. Sodium hydroxide will combine in a 1-to-1 ratio. And now for our phase, hydroxide is usually insoluble, but sodium is always soluble, so that makes this aqueous. All right, so these two are going to react to produce two things. First, liquid water, and now we have to deal with this enigmatic salt. But we know that our salt is going to be made up of our metal cation getting paired with the anion that our acid structure is based off of. So our salt is going to be sodium chlorite, and you can see sodium has a charge of +1, chlorite has a charge of -1, so these come together in a 1-to-1 ratio, NaClO2. All right, so these, we've written out our reactants, we've written out our products. We do not yet know if our work is done because we need to balance this chemical equation, right? So we have to take a chemical inventory of everything in all the atoms in our chemical reaction. So we have hydrogen, chlorine, oxygen, and sodium. Hydrogen, chlorine, oxygen, and sodium. Na. All right, so on our reactant side, we have 1 hydrogen from chlorous acid plus 1 hydrogen from sodium hydroxide. There's 1 chlorine, 2 oxygens in chlorous acid, 1 oxygen from sodium hydroxide, and then 1 sodium ion on the reactant side. Now on the product side, 2 hydrogens from water, 1 chlorine from sodium chloride. We have 1 oxygen from water plus another 2 from sodium chloride and 1 sodium. And you can see that our chemical equation is balanced, so we don't have any more work to do. That is our answer. And again, so a couple things. Don't overthink it. If you're taking the test and there's a problem, a balancing equation problem where everything comes out to be, you don't have to add any stoichiometric coefficients, don't look the gift horse in the mouth. Just take it. I wrote an easy problem. I've seen students semester after semester, when I give a problem that once you just write the products and reactants that it's already balanced, just throw a number in there because they just don't trust their gut, or they think there must be some trick. Trust yourself. If it adds up and it makes sense, roll with it. I will totally do that. I have in the past, I will in the future, and who knows, I might even on this exam. A second thing that I want to point out, because you may be wondering, well, how am I going to run how can I ask you to balance a chemical equation on a digital test, right? And there's and you've seen this on exam 1, but what will happen is I will ask you to enter the stoichiometric coefficient, or Shentz. All right, so like I could ask you to enter 1 or more of these, and in this case, the stoichiometric coefficient for every species, every molecule in the species is 1. So I could say, on the exam 2, it could be formatted like this. Chlorous acid reacts with sodium hydroxide to produce water and a salt. What is the stoichiometric coefficient of chlorous acid in the balanced chemical equation? That's one way I could do it. Or I could say, what is the stoichiometric coefficient of, I could ask for all of them. Chlorous acid, sodium hydroxide, water, and the salt. And so you'd have to enter the individual numbers by each one. So again, if you're wondering, how am I planning on testing balancing chemical equations, that's one of the ways I can do it. The way I'll do it, actually. So either ask for 1 or multiple. All right, so that was definitely a warm-up example, right? Let's do another one. Let's do the write a balanced chemical equation for the reaction between sulfuric acid. Oops. sulfuric acid and barium hydroxide. All right, so sulfuric acid and barium hydroxide. So again, we're in the same boat where we have to figure out what our acid is, and an ic acid came from an ion whose name ends in 8. So this is from the polyatomic ion sulfate, and sulfate has a chemical equation, SO4 with a charge of -2, and that charge is crucial because that tells us how many hydrogen sulfuric acid has. So sulfuric acid is H2SO4. All our acids are aqueous, and this is an example of a diprotic acid because we have 2 protons in this molecule. All right, 2 protons reacting with barium hydroxide. Now barium, we can figure out its charge from the periodic table. It's a +2. Hydroxide, as we already know, OH minus. So this will combine in a 1:2 ratio with barium. 1 barium cation will pair with 2 hydroxide anions so that it's net neutral. And hydroxide is usually insoluble, but it's slightly soluble with barium, so we're going to write it in the aqueous phase. Now the products here for this reaction, the products for every neutralization reaction are always water, H2SO4 is not water, H2O, now and a salt, right? And this salt is made up of barium and sulfate, and you can see that barium is +2, sulfate is -2, so these will combine in a 1:1 ratio, BaSO4. All right, now sulfate is on the usually soluble list, but it's insoluble when paired with barium. Oops, so this will not be an aqueous salt. This will be a solid salt. It's not soluble in water. All right, now we need to balance our chemical equation. So we have hydrogen, sulfur, oxygen, barium. On both sides of this reaction, hydrogen, we have 2 coming from sulfuric acid plus another 2 coming from barium hydroxide, 1 sulfur, 4 oxygen from sulfuric acid, 2 oxygen from barium hydroxide, and 1 barium. All right, now on the product side we have 2 hydrogens, 1 sulfur, 1 oxygen from water, 4 from barium sulfate, and 1 barium. All right, so you'll notice that barium is already balanced, sulfur is already balanced, hydrogen and oxygen are not. When I look at these two, hydrogen seems a lot easier to balance than oxygen, right? 2 goes into 4 twice, so I'm just going to multiply H2O by 2, and I'll worry about oxygen later. Now we have 2 oxygens coming from water and 4 hydrogen, and you'll notice that this is our Disney ending. We slap that 2 on there, and it balances hydrogen and oxygen in one foul swoop. So that is the balanced chemical equation for the neutralization reaction that occurs between barium hydroxide and sulfuric acid. All right. Okay. So let's take this to the next level. All right. Now that we know kind of how the nuts and bolts of how neutralization reactions work, let's start seeing some next level problems. All right. So consider the following example. Let's see. So 25.00 milliliters of 3.0 molar hydrochloric acid is mixed with where was, okay, there we go. Was mixed with 25.00 milliliters of lead 2 hydrox. Oh wait, hang on. Hang on one sec. With, sorry, 25.00 milliliters of 3.0. No, hang on. We're going to make this 2.5. .5 molar of sodium hydroxide. Lasso tool is going to save this from being sodium hydroxide. Alright, so 25 mils of 3 molar hydrochloric acid is mixed with 25 mils of 2.5 molar sodium hydroxide. Part A. Part A is write a balanced chemical equation. Part B. Determine the theoretical yield in grams of water. All right, A, B, and then part C. The density of water is 1.008 grams per milliliter. What is the total volume of the solution once the reaction is complete? All right. Okay. This problem took a while to write. It's going to take some effort to solve. And if you find yourself looking at this and going, I don't know where to start, or feeling overwhelmed, because you've never seen a problem like this before, my response to that, to that feeling, is that is good. That is good, and here's why. You will, on exam 2, and exam 3, and exam 4 in the final, come up against problems that you've never seen before. You've never seen this before. And so this is a simulation of that feeling that you will have on the exam. All right? You will have this, you'll experience this on the exam, guaranteed. Now, here's how you solve a problem that you've never seen before. All right? That is the experience I'm going to give you over and over in lecture, not to memorize this type of problem, but to learn how to think your way through it. All right. So, let's they can just leave a message. No idea who that is. All right. So let's start with step 1 of this situation. Let's write a balanced chemical equation. So first off, we're dealing with hydrochloric acid. So hydrochloric acid. All right. Now, anytime you're dished out a hydroic acid, that means the anion on which this acid is based ends in an ide. All right. So we're dealing with chloride, which is just Cl minus, right? It's when atomic chlorine becomes anionic. Cl minus. So first off, that tells us that our acid here is HCl. All right? That'll be in the aqueous phase. Now let's take a look at our base. Here we have sodium hydroxide. Sodium is a cation with a charge of +1. We get that from the periodic table. And hydroxide, OH minus. So these combine in a 1-to-1 ratio. Sodium is always soluble, so it doesn't matter what you pair it with. It'll be in the aqueous phase. Oh, hang on. Sorry, I wrote that in the wrong layer. All right. These two react to produce liquid water and a salt based on the anion left over by the acid and the metal in your metal hydroxide base. So our salt product will be NaCl, and that is in the aqueous phase. All right, so this is our chemical equation. We need to balance it now. All right, so we have hydrogen, chlorine, sodium, and oxygen. We have 1 + 1 hydrogens, right? 1 from HCl, 1 from sodium hydroxide. On the reactant side, 1 chlorine, 1 sodium, 1 oxygen. On the product side, we have 2 hydrogens, 1 chlorine, 1 sodium, 1 oxygen. So we're balanced. We have our balanced chemical equation. Part A is good to go. Part A is good to go. Now let's look at part B. We're asked to find the theoretical yield in grams of water. And we've been given that we have 3.0 molar HCl, 2.5 molar sodium hydroxide, and we have 25.00 milliliters of each. All right, this is a limiting reactant problem. Anytime you're given initial quantities of more than one reactant, then it's a limiting reactant problem. You have to figure out which one is going to run out first. To do that, you need to do the calculation for grams of water that could be produced by each quantity. Whichever value is lower, that is your theoretical yield, and it came from your limiting reactant. Notice that in this problem, I didn't say the word limiting reactant anywhere. All right, so it's not always going to be, in an exam context, a dead giveaway like, solve this limiting reactant problem. You need to be able to recognize the situation and know what to do. All right, so be ready. So now let's solve this. Now, you may be noticing, if I had given you grams of each of these, you know exactly what to do, right? You take grams, convert them to moles, and then you're off to the mole-to-mole conversion party. Here, you'll notice that we're given molarity and milliliters. Isn't there a way to use division to find the limiting reactant? Sorry, that's a question coming in. Isabel, it's totally possible. I don't know a method off the top of my head, but that doesn't mean there isn't one out there. So I don't know one, but that doesn't mean it doesn't exist or can't exist. So yeah, maybe I could stand to learn a thing or two. So, but I do know how to solve this problem one way, and that's the way I'm going to do it. Now, again, if I had given you grams of HCl, grams of sodium hydroxide, you would have been solid. If you're wondering, what do I do with this whole molarity situation? Remember that molarity has an equation. Molarity is equal to moles of solute over liters of solution. All right, and you'll notice that here we've been given molarity. We kind of have been given liters, right? We can convert from milliliters to liters. And so if you know your molarity and your volume in liters, if you multiply both sides of this equation by liters, you can solve for moles. Moles, your moles of solute, will be equal to your molarity times your volume in liters. So before we can use these two quantities, we need to convert from 25.00 milliliters to liters. You put milliliters in the denominator, liters in the numerator. 1 milliliter is 10 to the negative third liters. And so you crunch the numbers, and my calculator will tell me that my answer is 0.25, but you got to watch for sig figs. 25.00 has 4, and so we need 4 in our answer. We only have 2 right now, so we have to add a 0, 0, and then our unit. All right, so now that we've converted liters to milliliters, we are good to start solving this problem. Now, I'm going to start with HCl. Make this just slightly bigger here. So we've got 3.0. Now, molarity, whenever I use molarity in a math problem, when I'm like working a problem, I break it up into my numerator and denominator, just because that capital M, it's really easy for me to get that I have liters in the numerator there. And it'll make it easier to cancel, right? So if I multiply this by my volume in liters, which we already converted, it's 0.02500 liters. You can see that liters here in my denominator cancels with this liters, this volume that I'm multiplying by, and now we're just left with moles of HCl. We're not trying to find moles of HCl though, we're trying to find moles of water, so I'm going to put moles of HCl in the denominator, moles of H2O in the numerator. This is a 1 to 1 mole ratio because of my balanced chemical equation. So moles of HCl cancel. And then finally, because I'm trying to find my theoretical yield of water in grams, I'm just going to go the distance and convert from moles of water to grams of water. And if I've calculated the molecular weight of water before, it's 1 mole of water has a molecular mass of 18.016 grams. So moles of water cancel. And now we're good to crunch our numbers. Okay, so we've got 3 times 0.025 times 1 divided by 1 times 18.016. So this comes out to be 1.3512, right? Sig figs wise, we got to roll with our least amount of sig figs. That's that 1.3. Oh, sorry, the 3.0 is 2 sig figs. 5 is going to round up. So this will come out to be 1.4 grams of H2O. All right. We don't know if that's our answer. To determine our answer, we've got to multiply 2.5. We've got to do the same calculation for sodium hydroxide. And actually, I'm going to scoot this down just so I don't get crowded later. All right, 2.5, and this is moles of sodium hydroxide over liters, multiplied by our volume, 0.02500 liters. Our volume cancels. Next, we convert from moles of sodium hydroxide to moles of H2O, 1 to 1. Again, because we get that from the balanced chemical equation, 1 mole of sodium hydroxide produces 1 mole of water. So moles of sodium hydroxide cancel. Then finally, 1 mole of H2O has a mass of 18.16 grams of H2O. Moles of water cancels, and we are ready to crunch our numbers. So we have 2.5 times 0.02500 times 18.016. Again, we're limited to 2 sig figs. My calculator's telling me this is equal to 1.126. You count off your first 2 sig figs. 2 is going to round down. So 1.1 grams of water. And because this is smaller, this is our theoretical yield. All right, that is our theoretical yield of water. Okay, so we balanced the neutralization reaction, a skill we just acquired. We did a limiting reactant problem that was deceptively couched in an acid-base reaction, right? With molarity and volume, so something that we haven't seen a ton before. But now this third part is something we haven't ever seen before, right? Part C, they tell us the density of water is 1.008 grams per milliliter. What is the total volume of the solution once the reaction is complete? And here is where we're standing right now. So this is part C. What is the total volume? What a weird question. Well, what is contributing to the volume? Well, think about it. We mixed 25.00 mils of HCl with 25.00 mils of NaOH. So you might be thinking, let's add these two together, right? And that'll be our total volume. And you're on the right track. We did mix these two volumes together. But we also made, in the course of this reaction, we produced 1.1 grams of water. And this is why we were given the density. Our total volume is going to be the HCl together with the sodium hydroxide plus the amount of water we made. We know the mass in grams, the theoretical yield, but we need to use the density of water, which is equal to grams over milliliter, to find our volume. We've been given the density and we know the mass that we made, so we need to solve for the volume. All right? So we've got a little bit of math to do. We're going to start by multiplying both sides of this equation by milliliters. All right? That gives us a rearranged equation. Now milliliters, or volume in milliliters, times density is equal to mass. We want to get milliliters isolated on one side of this equation, so we divide both sides by density, and we get milliliters, the volume of water in milliliters, is equal to the grams of water divided by the density. We know our grams of water produced, 1.1 grams. We know the density because we were given the density, 1.008 grams per mil. 1.1 divided by 1.008 is 1.09 milliliters. Let's see, I'm a little crowded here. But you'll notice we can only keep 2. And when you round this 9 up, it's going to become a 1. So we have made 1.1 milliliters of water. So now we can calculate our total volume, because we take the volume of HCl, 25.00 mils, plus the volume of sodium hydroxide, 25.00 milliliters, plus the volume of the water that was made over the course of this reaction, 1.1 milliliters, and we add these all together. So when you punch this into your calculator, it'll tell you that, whoops, not 25, that we get a volume of 51.1, but you have to ask yourself, is that correct from a sig figs perspective? And so when you look, we just did an addition, right? 25.00 is precise to the second decimal place, but 1.1 is precise to the first decimal place. And when you're adding, you go with your least precise number. And when you look at your answer, its last sig fig is in the first decimal place. So we're good. There's no need to round. We have the correct number of sig figs. All right. So that is that question. Sorry, my apologies. Oh, that's scary. That's my voice. Okay, sorry. I was just checking my phone because my something happened with my computer network, so I lost the live feed on my secondary monitor. So I'm using my phone now. So if you see me looking down at my phone, it's because it's turned into my my access to your comments. I see nobody's left a comment in between now and when I all right, sorry. I'm just getting everything back online. Close. All right, we're good. Okay. So that is an example of seeing kind of a neutralization reaction in the wild. Here's the thing. It's very easy to compartmentalize things in your mind, like stoichiometry, acid base, molarity is all these different things, but the reality is they all connect. All right, so you should totally expect on the exam to see these kind of amalgam problems where it's limiting reactant with molarity, with neutralization, all of these things coming together. All right, it's part of what makes chemistry challenging, but it's also part of why this is on the MCAT, for example, or the DCAT. I don't know the name of the veterinary school equivalent, but it involves critical thinking. It involves diagnostic thinking, and so that's why it's like this. All right, let's see. We've got about 27 minutes. All right, we're gonna set up. We may not finish chapter 4 today, so. But we're going to get close. We've got... Kate, that is correct. So Kate just asked, solids don't add to the total volume. Is that correct? And that is correct. Solids are not part of the solution, so they don't contribute to that volume. They are kind of off on their own. Now, we're going to do a subtle shift here. We're still going to be dealing with neutralization reactions, but we're going to shift our focus to a type of experiment known as a titration. All right, a titration experiment. Titrations is a type of experiment. I believe we'll at least do one E-lab involving titration. Sorry, that was a little more full than I thought it would be. And there's many different types of titrations. It doesn't have to be an acid-base reaction, but often we use titrations in an acid-base context, and so that's why we're introducing it here. Now, in a titration, you're going to use a known quantity. This could be the mass of a solid. All right. It could be the mass of a solid. Let's see. Or it could be, or I don't know why I closed my parentheses. Actually want these still open. The mass of a solid, or a volume of a solution. With a known concentration. All right, to determine an unknown quantity. And here, your unknown quantity could totally be a mass, or, or you could use this to determine, should say not the, an unknown concentration of a second solution. All right, that is what a titration experiment is. You're taking some known quantity and you're using that known quantity to determine an unknown quantity. Now, you might be wondering how. I'm so glad you asked, because that is exactly what I'm going to show you. All right, so, for example, so here's kind of how a titration is set up. So these are typically done with a burette, which are these long kind of they kind of look like graduated cylinders. They're long, they're tall, and then at the bottom there's this thing called a stopcock, which controls flow. You can turn on and off kind of the flow of solution, and inside your burette you'll typically have your solution. All right, actually I shouldn't have filled that to the top. Let's be a little more accurate. So up in here, you've got your solution. So this, for example, there we go. You fill, so this is a burette. It drains from the bottom, and it's filled with your titrant. All right, Your titrant is your solution of known concentration. All right, so you've got your titrant, your solution of known concentration, and then beneath the burette, you'll have, usually in an Erlenmeyer flask, that's my really crummy drawing of an Erlenmeyer flask. There's some perspective. Down in the Erlenmeyer, you'll have your solution of unknown concentration, which is called your analyte. There we go. So this right here is your analyte. And this is your solution with an unknown concentration. And typically, in addition to your analyte, you add what's known as an indicator. And an indicator is a substance that will change colors based on pH. So when your reaction is over, it'll change color, because what we're going to be doing is we're going to be adding from our burette, we're going to add our titrant until, so we've got our initial volume here. We're going to add the titrant until the indicator changes color, and then the burette will give us our second volume. And when that solution changes color, we stop adding the titrant because we've known we've added enough titrant to react completely with the analyte, so there's no more analyte left in solution. So our indicator here, sorry, let me just add this to be complete. Changes color when the reaction is complete. All right. The indicator changes color when the reaction is complete, so you know when to stop adding your titrant. And what's recorded, so you will know so here are your known quantities when the experiment is over. You will know your molarity of titrant, you will know your volume 1 and volume 2 of titrant, all right? And there's one additional piece of information you will know when this is over. All right, the one additional piece of information you will know that you'll be given in problems like these is you will also know the volume of your analyte. And from these 4 pieces of information, you will be asked to find the molarity of your analyte. Which again, by way of reminder, molarity is moles per liter. And notice, you already know the volume of your analyte, so you're actually given your denominator. You need to find your moles of analyte using this information here, your molarity of titrant, your initial and final volume. All right, so this is kind of the strategy. This is the conceptual breakdown. I'm going to walk you through step by step an actual titration problem, one that's comparable to that you could see on an exam, for an example. All right, let's do a titration problem. So here's how it will be laid out for you, or how it could be. Let's see. 10.00 milliliters of sulfuric acid is titrated. Oops, not treated. Is titrated with 1.00 molar sodium hydroxide. The initial burette reading was 0.27 milliliters. The final was hang on. There we go. The final was 18.80 milliliters. Determining it's not a word. Determine the molarity of H2SO4. All right, again, there's some things we have to keep in mind. First things first, we need to find, we're being asked to find, in this problem, the molarity of sulfuric acid. Right? Anytime you're asked to find a quantity that has a mathematical formula, you should write that out. Sorry, Keith, I just saw your question. It totally will be. Keith just asked if titration will be on exam 2. It 100% will. All of chapter 4 will be on exam 2. All right, so we're being asked to find the molarity of sulfuric acid. Molarity is equal to moles of H2SO4 over liters of solution. And the cool thing is, we've already been sort of given the liters. It's a little bit of a problem, right? Because it's in milliliters, so we've got to do that conversion. But once you do, to convert 10 milliliters to liters, then you've got your denominator. 1 milliliter is 10 to the negative third liters. And so our volume in liters will be 0.01000 liters. So we've got our denominator. We need to find our numerator, right? If we can find the moles of sulfuric acid, then we'll pop that in the numerator, we'll be able to calculate it. I want to tell you something. It is impossible to solve a titration problem. Well, every titration problem I will write you on exam 2, you will need a balanced chemical equation. All right? You will need a balanced chemical equation to solve. Here's the reason why. When you look at what is given, other than the denominator of our molarity, right? We're given molarity of sodium hydroxide, and then the V1 initial volume and V2 final volume for sodium hydroxide. We have all the information we need to find moles of sodium hydroxide, but how do you convert from moles of one thing to moles of another? You need a balanced chemical equation. So if you're going to solve this problem, you need to balance your chemical equation and then use that mole to mole ratio to convert from moles of NaOH to moles of H2SO4. All right? So for our future use, let's go ahead and balance it now. I would recommend writing a balanced chemical equation before you do anything when you're dealing with a titration problem. All right, so we have sulfuric acid, H2SO4, reacting with sodium hydroxide. Now, you may be caught for a minute and go, wait a minute, what are our products? Josh, you didn't tell us our products. And the cool thing is they don't have to, because we have an acid reacting with a metal hydroxide base. That is a neutralization reaction. Every neutralization reaction produces water and a salt. What is that salt, you might ask? That salt is made up of the cation from the metal hydroxide and the anion that's left over after you strip away all the protons from the acid. So for this reaction, the salt will be sodium sulfate, which is aqueous because sodium is always aqueous, always soluble. All right, so there's our balanced chemical equation. I don't know if it's balanced yet. I don't know if it's balanced. Let's see. Let's find out together. All right, so actually, hang on, I just got to get this all in one layer. There we go. I don't know if this is balanced. I need to check. I can't get lazy. So we've got hydrogen, sulfur, oxygen, and sodium on both sides of this reaction. Hydrogen is, we've got 2 plus 1 on our reactant side, 1 sulfur, 4 oxygens in sulfuric acid plus the 1 from sodium hydroxide and 1 sodium. On the product side, 2 hydrogen, 1 sulfur, 1 oxygen from water, 4 from sulfate, and 1 sodium. When I don't have 1 sodium, I have 2, right? 2 from sodium sulfate. Now when I look what's out of whack in this situation, sodium jumps out and it looks easy enough to solve. So let's go ahead and multiply sodium hydroxide by 2. So sodium balances out. Let's see, so I multiply sodium by 2. Now I have 2 oxygens coming from sodium hydroxide as well as 2 hydrogens. Now on my reactant side, I'll have 2 plus 2 hydrogens. I'll have 4 plus come on, Photoshop. Oh goodness. Okay, hang on 1 second. Photoshop's freaking out. There we go. Let's try 4 plus 2 oxygen. And 2 sodium. All right. Now sodium's balanced. I've got to work on oxygen and hydrogen. All right. Hydrogen looks simple enough. 2 goes into 4 twice. So I'm going to multiply H2O by 2. This will balance my hydrogen. Let's see what it does to oxygen. Now I'll have 2 oxygen plus 4. Everything balances out. This is my balanced chemical equation. Oh, let me add my 2 back to H2O. There's my balanced chemical equation. All right, I'm going to need this to solve. All right, I'm going to need this to determine my molarity of sulfuric acid. Again, I need to know moles of sulfuric acid. That's what I don't know right now. So let's look at what we do have. We do have, I'm just going to rewrite some of our given information from the previous slide, so we have it for context. We have been given let's see. Okay, so we know our molarity of sodium hydroxide. It's 1.00 moles of NaOH per liter. All right. So if we want to find moles of sodium hydroxide, we need to know what our volume is, right? And to find our volume of NaOH, you take your final burette reading, V2, and subtract your initial burette reading. All right? Our final reading, because the volume delivered is the difference between the final and initial. So the final reading was 18.80 milliliters. The initial reading was 0.27 milliliters. When I take this difference, 18.8 minus 0.27 comes out to be 18.53 milliliters. All right? Now, you'll notice that we've found our volume of sodium hydroxide in milliliters, but for molarity it's in liters, so we actually need to do a unit conversion here. 18.53. We need, to convert from milliliters to liters. So mils in the denominator, liters in the numerator. 1 milliliter is 10 to the negative third liters. milliliters cancel. And now that we have our volume in liters, we can use it to find the moles of sodium hydroxide, right? We can multiply this by 0.01853 liters. So these cancel. Next, now that we have moles of sodium hydroxide, we can convert from moles of NaOH to moles of sulfuric acid. You'll recall that's what we need to find our molarity, right? That's our numerator. And our balanced chemical equation tells us that 2 moles of sodium hydroxide react with 1 mole of sulfuric acid. So moles cancel moles, and we don't need to convert to grams because we're not asked for that. So we have 1 times 0.01853 divided by 2 is, let's see, 0.00927 once you round for sig figs moles of sulfuric acid. All right, because again, you got to roll with your fewest amount of sig figs. All right, we're almost there. We're almost to the end. Now that we know how many moles of sulfuric acid we have, we can solve for our molarity. Because molarity of sulfuric acid is equal to moles over liters. And we have, as we just calculated, 0.00927 moles of sulfuric acid. And we have a volume of 0.01000 liters. So we divide our moles by our volume in liters, and we get 0.927 molar is the concentration of our analyte solution, sulfuric acid. All right, so that is titration. There is one, Kate, great question. So there's one last thing I want to say about titration before we end lecture today. You will find, and even in the lab manual, if you look at the lab manual for the FLC lab, there's a titration lab. That'll say, if you're doing a titration calculation, just use the dilution equation. M1V1 equals M2V2. All right. I have to issue a caveat emptor, which is Latin for buyers beware. All right. Oops. Sorry, I wanted that to be red. So something you should note. Oh, come on, Photoshop. It's freezing up on me. All right, well, so I'm gonna say it with my words then, and then I'll write this at the beginning of next lecture. The dilution equation M1V1 equals M2V2 only works if there is a 1-to-1 ratio between if there's a 1-to-1 ratio in the balanced chemical equation between your analyte and your titrant. All right. So if your acid and base have a 1-to-1 ratio, molar ratio, in your balanced chemical equation, the dilution equation will work. All right. If you do not have a 1-to-1 ratio, this will give you the wrong answer. And I'm going to make you a promise right here, right now. Every titration problem that I give you on exam 2 will not have a 1-to-1 ratio in the balanced chemical equation for the reaction between the acid and the base. So if you use the dilution equation on the exam, you'll get the wrong answer. All right? So I want to be as upfront with you as I can. The dilution equation is a special case only for 1-to-1 ratios. But if a 1-to-1 ratio, if you don't have a 1-to-1 ratio, then it will not work. So sweet, Photoshop got unfrozen. This only works when there's a 1-to-1 ratio between titrant and analyte. All right. So if you see there's a 1-to-1 ratio between titrant and analyte, you can use this, but caveat emptor, buyers beware, I will not be giving you those on the exam. You'll have to balance a chemical equation on exam 2 to do the titration problems. All right, we're gonna wrap things up there. On Wednesday in lecture, I'm gonna start off by doing a titration example. So you'll get another rep in with this, and then we just have one last topic to cover. It's just a type of acid-base reaction, but it's not going to be earth-shattering. So we'll wrap up Chapter 4 on Wednesday, and then dive into Chapter 6. Any of the Chapter 6 material we cover will not be on the test. The exam cutoff is Exam 4. Keep an eye on Canvas. Later today I'll be posting the statistical breakdown for all the points involved. All right. I will, don't forget, we got office hours tonight. I'm just going to start probably for the first hour-ish lecturing on gas laws, and then it'll be open office hours. So you'll be able to hit me up with all your questions, probably starting around 8-ish. At 7, I'm going to be lecturing. Then I'll probably be done around 8. All right. All right. Dudes, thanks for tuning in. I'll see some of you later tonight. The rest of you I'll catch Wednesday morning. Not morning, afternoon, 1 p.m.